Okay, let's get started for the day. We had looked at the properties of the region of convergence, and let me recall one of the properties. One of the properties was if e to the j omega belonged to the region of convergence, then we can let z equal to e to the j omega. In this case, we get x of z evaluated at z equal to e to the j omega, and this we denote it as x of e to the j omega, and this of course is sum over all n x of n. It was z to the minus n. Now we have let z equal to e to the j omega. Therefore, this now becomes e to the minus j omega n. This was one of the properties, and then if you recall, this was called as the discrete time Fourier transform and abbreviated as DTFT, analogous to the abbreviation we had used for the continuous time case, that was continuous time Fourier transform CTFT. This is the discrete time counterpart of that. Before we get into more details of this, let us immediately deduce one consequence of e to the j omega belonging to the region of convergence. Therefore, we have x of e to the j omega to be n between minus infinity to plus infinity, x of n e to the minus j omega n, and we can do this because the ROC contains the unit circle. Therefore, the DTFT exists, and the criterion that we have been using is absolute convergence. Therefore, this means that this will be finite. So, this is nothing but n going from minus infinity to plus infinity, x of n e to the minus j omega n, and as we had noted before, the absolute value of the sum is less than or equal to sum of the absolute values. So, for this is less than or equal to this, and absolute value of the product is the product of the absolute values. Therefore, this becomes this, and this is less than infinity, and this of course is 1. Therefore, what we have is the above implies sum over all n this is less than infinity. Moment you have the fact that the unit circle belongs to the region of convergence, immediately that leads to this conclusion. So, the implication of this is that x of n belongs to the class of absolutely summable sequences. Therefore, if the region of convergence includes the unit circle, then x of n belongs to the class of little l1. Little l1 is of course the class of absolutely summable sequences, and this is the equivalent of what was happening in the continuous time case. If the j omega axis is part of the ROC, then the function x of t is absolutely integrable, and it belongs to the space of cap L1, the class of absolutely integrable functions. So, now let us look at the DTFT a little more. So, we have x of e to the j omega by definition is this, and from this definition if you replace omega by omega plus 2 pi, you get x of n e to the minus j, wherever omega is there, you are going to replace omega by omega plus 2 pi, and this of course is exactly the original DTFT. And hence this is the same as x of e to the j omega. So, this is a function that is 2 pi periodic. Remember, the continuous time case, x of t had CTFT x of j cap omega, and that was an aperiodic function in general. The continuous time function was aperiodic, its transform also is aperiodic. Whereas here in the discrete time case, you have in general a sequence x of n that is aperiodic, but its transform, the DTFT, is periodic with period 2 pi. And there is another way of seeing this. We are motivating the DTFT as the Z transform evaluated around the unit circle, assuming of course the ROC contains the unit circle. Therefore, this is omega equal to 0. So, you are obtaining the DTFT by taking x of z, and then you are evaluating this around the unit circle, and you will hit pi, which is the same as minus pi, and if you complete the circuit around the unit circle, you will also hit 2 pi. Therefore, the periodicity of the DTFT is also evident from this geometric interpretation, where you are evaluating the Z transform around the unit circle. Therefore, if you keep going around the unit circle, it is clearly periodic with period 2 pi, and we saw this algebraically here, and this is the geometric interpretation of that fact. Sometimes the notation x of omega is also used for the DTFT. And note that omega equal to 0 corresponds to z equal to 1, right. So, this is also the same as z equal to 1, this point. And omega equal to pi, which is also the same as minus pi, corresponds to z equal to minus 1. Therefore, this point, which is omega equal to pi, which is the same as omega equal to minus pi, this corresponds to z equal to minus 1. And if you use the notation x of omega for the DTFT, and then if you evaluate this at omega equal to 0, you are looking at notationally something like this. On the other hand, if you are using the notation x of e to the j omega, and then you are evaluating this at omega equal to 0, notationally you are looking at x of 1. and this is the same as x of z evaluated at z equal to 1. So, either notation is fine, but you have to be careful as to which notation you are using, so that you are not tripped into thinking this x of 0 is x of z evaluated at z equal to 0, that is all. As long as you are clear as to what notation you are using, everything should be fine. The notation x of e to the j omega has the advantage that it shows up the periodicity of the DTFT explicitly, because wherever omega is there, if you replace omega by omega plus 2 pi, you get exactly the same thing. Therefore, the 2 pi periodicity of the DTFT is evident from x of e to the j omega notation. And if you use this particular one, this is also used in some contexts. Sometimes it is inconvenient to write x of e to the j omega. So, even in the later development, we will use x of omega notation when it is more convenient to write it out. And all of this parallels what is happening in the continuous time Fourier transform case. You had the bilateral Laplace transform x of s, and then if you replace s by j cap omega, you get x of j cap omega, which was the notation used for CTFT. You also use the notation x of cap omega by itself to denote the CTFT. The x of j omega notation had the advantage that it made explicit that it was obtained from the bilateral Laplace evaluating that along the j omega axis. Now, let us look at x of n, which is a to the n u of n, and we have seen this any number of times before, and we will continue to beat this example to death by the time we are done with this course. So, this is 1 by 1 minus a z inverse. So, this is mod z greater than mod a, and then for simplicity I am showing the pole to be real valued and positive. So, this is z equal to a. Of course, there is a trivial 0 at there is also a 1 trivial 0, and this is the circle mod z equal to mod a. All right. Now, suppose we have mod a to be less than 1. If mod a were less than 1, then this will be the unit circle. So, this is the unit circle here, and the ROC is mod z greater than mod a, and hence e to the j omega belongs to the ROC, which is mod z greater than mod a, and hence you can get x of e to the j omega by wherever z is there, you can replace z by e to the j omega, and hence you will get this to be 1 by 1 minus a e to the minus j omega. Therefore, in this case the DTFT exists, and you can immediately guess what the other case will be. The other case is mod a greater than 1. Therefore, if we now take this case and then make it like this. Now, in this case, this is the pole which is outside the unit circle, and e to the j omega now does not belong to the ROC, which is mod z greater than mod a, and then this tells you that the DTFT does not exist. Suppose mod A were greater than 1, and in this particular case the DTFT does not exist because the ROC does not contain the unit circle. Suppose you want the DTFT to exist in this case, what change is required? Yeah, exactly. So, in this case, if you want the DTFT to exist, you want the ROC to be mod z less than mod a, right. Therefore, if we have minus a to the n u of minus n minus 1, and here the z transform of course is this, the DTFT will exist if mod a were greater than 1, because if mod a were greater than 1, the pole will lie outside the unit circle and the ROC will be mod z less than mod a, and in this case the unit circle will indeed belong to the ROC. So, moment the unit circle belongs to the ROC, the DTFT will exist. Therefore, if you had an anti-causal exponential and if you want the DTFT to exist, the pole should be outside the unit circle, whereas if the exponential were causal, you want the pole to be strictly inside the unit circle, so that the ROC will now contain the unit circle. And again, if you look at the sequence, for example, if you looked at 2 power n u of minus n minus 1, right. So, this sequence is, if this were the origin, all positive indices are 0. Now, you need to start substituting values of n that are negative. Therefore, when n equal to minus 1, this is half. When n equal to minus 2, this is 1/4, 1/8 and so on. So, this is how the sequence is, alright, and clearly this belongs to L1. On the other hand, if you had half to the n u of minus n minus 1, when you put n equal to minus 1, this becomes 2, 4, 8 and so on. So, clearly this is not an absolutely summable sequence. So, this is what is basically happening. So, if the pole is outside the unit circle, the sequence is anti-causal, when you put negative values of n, the sequence really will die down and become absolutely summable, as simple as that. You can also have an intuition as to why the DTFT exists in this case for cases where the pole is outside, for anti-causal sequences. So, we will revisit the DTFT later.